Okay, number one, they want you to use the rational root theorem to list all the possible roots. And then after that, they want you to find any actual rational roots. So remember, the rational root theorem, you're listing all of the possible factors of p, which is going to be the constant, and then divide that by all of the possible factors of q, which is going to be the lead coefficient. So the p is going to be 4, so all of the factors of 4 are 1, 2, and 4. And we're going to divide that by all the factors of 2. So we have 1, 2, 4, then 1/2. 2/2 is the same as 1, and 4/2 is the same as 2. So this is your list here of all the possible rational roots. Then it wants you to find the actual rational roots. So what we're going to do is we're going to graph this. Let's just clear this out. 2x to the third minus 5x plus 4. And see where the rational roots are. Well, we see that there's only one real root right here. And it looks like it's at -2. So let's just check at the table. Well, it's not -2. -2 would be -2. So this 0 right here looks like it's irrational. It doesn't look like it's rational. We can use the second trace 0 to see what that 0 would be. So left bound be under it, right bound above it. The 0 is at -1.886796, so it looks like it's an irrational value anyway. So when it asks you find any rational roots, remember these are all the possible rational roots. If none of these are on the graph, then there's no actual rational roots for this problem. Alright, number 2, we're going to do the same thing. So all of the factors of 10 is 1, 2, 5, and 10. And we're going to divide that by the factors of 7, which is 1 and 7. So our list is going to be 1, 2, 5, 10, and then we're going to do sevenths. 1 7th, 2 7ths, 5 7ths, and then 10 7ths. So those are all the possible rational roots. Now let's graph this and see which one of those, if any, are roots of it. Alright, so it looks like there's only one root right over here. That could be rational. We're not sure. So let's do second trace 2. Left bound, right bound, enter. So -0.921 roughly. And none of these are -0.921. These are whole numbers. This isn't close to 1, that's not close to 1, that's not close to 1. This is above 1, so no rational roots for this one either. Alright, they want you to find 2 additional roots given these. Now according to the conjugate root theorem, this one has to also have 14 plus root 2 as a root, and this also has to have positive 6i as a root. And these are your 2 additional roots of the function. And you're done. They're not asking you to find the polynomial function with these roots. They're just wanting you to list 2 additional roots. For number 4, they want you to give the other 2 roots, and this one is negative 13i, and this one's going to be 5 minus 10i. And then after that, they want you to actually write the polynomial function. So what we're going to do is we're going to build up this polynomial function with this pair of conjugate roots, which will give us a quadratic, and this pair of conjugate roots, which will also give us a quadratic. Now again, we're going to use the x squared minus the sum of the roots, x, plus the product of the roots. So if I'm going to add these 2 roots together, I get 0. So that means I'm not going to have an x term. Then I move on to the product of the roots. So if I multiply 13i by negative 13i, I'm going to have negative 169i squared. And because I squared is negative 1, negative 169 times negative 1 is going to be positive 169. And that's going to be your first quadratic. This one over here, when I add them together, the i's cancel and you're going to have 5 and 5 is 10. The opposite of 10 is negative 10. So we're going to put that for our x term. The product of these 2, remember we only have to do f and l and FOIL since they're conjugates. So 5 times 5 is 25. Positive 10i times negative 10i is negative 100i squared. The I squared is going to make this positive. So 25 plus 100 is positive 125. Then what you want to do, because you want to build this entire thing out, or expand it out, is multiply these 2 together. So I'm going to distribute these 2 terms into these 3 terms. So when I do that, x squared times x squared is x to the 4th. X squared times negative 10x is negative 10x cubed. X squared times 125 is 125x squared. 169 times x squared is 169x squared. 169 times negative 10x is negative 1690x. And 169 times 125 is 21,125. So when I add like terms, I'm going to have x to the 4th minus 10x cubed plus 294x squared minus 1690x plus 21,125. And that's our polynomial function. That's the answer. Number 5, Descartes' rule of signs. So what we want to do is we want to do a little sign chart for p of x and one for p of the opposite of x. So we're just going to write a list of signs. First for p of x, so positive, positive, positive. P of the opposite of x, what I'm going to do is I'm going to change the signs of any term that has an odd degree. This has an even degree, it's x squared, so I'm going to leave that positive. This is x to the 1. 1 is odd, so I'm going to change that to a negative. This is my constant, so I'm going to keep that positive. What you're going to do now is you're going to count how many times the sign changes. It doesn't change at all here, so that means I'm going to have 0 positive real roots. This changes once, twice. That means it's going to be 2 or 0 negative real roots. Number 6, find all of the rational roots. So what we want to do is we want to graph this. So 3x to the 4th. It doesn't look like there's a graph there. So let me just double check here. 3x squared minus 7x plus 10x. I typed it in right. Let's just look at the graph again. Let me zoom out just a bit. Yeah, it's way up here. You can see that it doesn't go through the x-axis at all anywhere. Let me zoom it back in, and then let me increase the window for the y's. Let's make it go up to 50. Go up by 5. Probably see the graph better this way. Yep. So it looks like that. So it's not going to go through the x-axis at all. So that means there's no rational roots. So no rational roots. All right, number 7, divide using long division. So it's going to be 3x minus 1, and then 6x cubed plus 7x squared plus 12x minus 5. All right, 3x goes into 6x cubed, 2x squared times. Then we multiply across, so 6x cubed minus 2x squared. Then we're going to change the signs down here and then add down. So we get 9x squared. Bring this term down. 9x squared divided by 3x is 3x. 3x times 3x is 9x squared. 3x times negative 1 is negative 3x. Change the signs. Add down. 15x divided by 3x is 5. We multiply, change the signs, add down, you get a remainder of 0. So this is your answer. Alright, for number 8, they want you to divide using synthetic division. So if we're dividing by x minus 1, we're going to use positive 1 for synthetic. And we want to account for every degree, starting with 5, going all the way down to the constant. So 1, x to the 4th is not there, so we're going to put a 0. X cubed is 1, x squared is not there, x is not there, and then we have negative 2. So bring the 1 down, multiply, add 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 down. So here's your constant, your x, x squared, x cubed, x to the 4th. So your answer is x to the 4th plus 1x cubed plus 2x squared plus 2x plus 2. No remainder. Number 9, they want you to describe the end behavior, and they want you to give the number of turning points. Alright, so this is x to the 4th. It's an even function. That means it's going to have the same end behavior on both sides. Either they're both going to point up or they're both going to point down. This leading coefficient is positive, so they're both going to be pointing up. So the limit as x approaches either positive or negative infinity of the function, this should be written as f of x, is going to be positive infinity. The number of turning points, we can graph it, see what it looks like. It looks like there's one turning point right over here, because it goes downhill and then it starts going uphill over here. So there's one turning point. Alright, number 10, a friend asks you to explain the conjugate root theorem. How would you explain it? Well, again, the conjugate root theorem states that if, and I'm just going to use notation here, but I'm going to explain it. If you have an irrational value, let's say a plus root b, and or if you have a plus bi, which is an imaginary. So if you have an irrational or an imaginary root, the conjugates of those roots, meaning a minus square root of b or a minus bi, will also be roots of the polynomial function. So if you have any irrational and or imaginary roots of a function, those imaginary or irrational values, roots, will also have their conjugates as being roots of the function. That's it.